About the thin film transistor. Is the TFT. TFT is different from normal transistors in VLSI in a sense that normal transistors, the thickness of the silicon wafer, first of all, is a single crystal of silicon, and the thickness is about more than 200 microns. Mostly it is 600 microns these days because the wafer becomes very large, like a 12-inch in diameter. So that's huge, And if the thickness is too thin, then it's going to be twisted during the heat cycle, warpage things. So we have to keep this thickness above a certain thickness, and normally it is about 600 microns. And if you are not going to carry out the severe heat cycles, then this thickness can be reduced to 200 microns. But mostly, typically, generally, it is about 600 microns. And then the transistors is going to be fabricated on the top surface, and the thickness of this top surface is just 10 microns, less than 10 microns. In other words, 590 microns is just a substrate. Single crystal silicon, but it's just a substrate. We are using top 10 microns from the surface for the transistor fabrication in normal transistor case. In thin film transistor, however, firstly we are going to use a glass. Okay? Basically it's a silicon oxide and it's amorphous. And then we deposit the silicon, which is the semiconductor material, for the transistor fabrication. And this silicon is usually we use a sputtering for the deposition of silicon on top of the glass, and the thickness is about less than 1,000 angstrom. That's a very, very thin, right? That's very, very thin. And with this, we're going to fabricate the transistors, and naturally, the transistor is going to be something like an island on top of the glass. It should be something like this. It's a kind of island, and each transistor is going to be connected according to our circuit design. Okay, so what's the difference between these transistors and these transistors? The typical difference, the main difference is that these transistors are floating. First of all transistors are floating. The transistors on this normal wafer, they are connected somehow on the body. and the silicon single crystal. But in this case, each transistor is separate from each other because they are built on the glass, and then physically the silicon thin film is removed to make it the island. And then they are going to be interconnected with the metal, just like the interconnection of the transistors in a normal wafer. Okay, so that is the big difference. And the second big difference is that in this case it's a single crystal, but in this case you cannot make a single crystal on top of the glass. You cannot. So either amorphous or at most you can make a polycrystal, polysilicon. But if you want to make a polysilicon, normally you have to heat up above 700 degrees centigrade for at least 8 hours, something like that. Okay, normally to make amorphous silicon turn into the polysilicon. You need this treatment, but unfortunately you cannot do this because the glass, which is essential for the display devices, it should be transparent. The substrate has to be transparent, so we have to use the glass, and then this glass cannot put up with this temperature. So that's why we have been using the amorphous silicon for the TFTs. Okay, we cannot use the polysilicon for the TFTs in the display devices for the TFTs. Well, so we need, if you want to use a polysilicon TFTs, then you need low temperature polysilicon. This is the LTPS, low temperature polysilicon. This is a special technique. Okay. Now, before I go into the details of this LTPS process, which is the main topic of this last lecture, I probably have to introduce some of the problems that might happen when we have this floated transistors. Okay? And that has been studied early 1900, and that the topic related with this is SOS. We call that the silicon on sapphire. How many P's? No. Okay. The reason why we have two P's there. The reason why we want to work on the silicon on the sapphire is that the lattice mismatch between the silicon and sapphire is less than 0.2%, which means we can grow epitax layers, epilayers. In other words, if you have a sapphire here, sapphire is basically aluminum oxide. It's aluminum oxide, so it is insulator. Okay, if you have a single crystal of sapphire, and then you put silicon on top of this, And this structure, crystal structure of this, is very close to the single crystal. So we can extend the ideas, the transistor performance ideas, electrical properties of transistors, to this silicon, which is especially deposited on top of the sapphire. And this sapphire is the insulator. So it's, in terms of the electrical characteristics, this SOS transistors is very much like this transistor TFTs, except the fact that this TFTs is amorphous or polycrystalline most, but in here, the SOS, the silicon may be called the pseudo single crystal, very close to a single crystal. So it is easy to extend the idea of electrical performance of the transistors to this SOS, which we have discussed in the class, right? Let me just introduce some of the subtopics that we can think out of this case. Well, the problem areas, let me just introduce the problem areas and then problem areas. And then if you are interested in this SOS, you may go to the literature to find the details of this. But nobody is working on SOS anymore. It has been stopped late 1900s because it's not worthwhile because of this problem. The number one, low mobility as film thickness goes down. Okay? And then leakage along silicon and silicon oxide, aluminum oxide, the substrate. Aluminum oxide interface. And then edge effect. Or silicon island. We have to call this silicon islands because electrically it is separated. And then floating substrate effect. In other words, in this case, we can put the bias on this substrate, okay? But here, there's no way to apply the general substrate bias for the all transistors. So with that, we call it's floating. And then the control of threshold voltage and so threshold current. Those problems, many scientists, researchers have been working on those problems, but the main thing is it cannot be industrialized because the electrical performance of this SOS is inferior to the transistors which has been built on the single crystal substrate because of this problems. And secondly, the sapphire is very expensive. Okay, so there's not really practical in an economic sense to put this thing into industry. So a lot of research work has been done, but it's just research. Okay, it never been industrialized. And today, let me just focus on the TFTs. TFT is different from the SOS in the sense that TFT is essential for the display devices. And then, as you know, these days, nobody uses the CRT for the displays. We have to use the flat panel displays, which is LCD mostly. And that is going to be changed to the OLED, okay? We call the AMOLED. Which is AMOLED. That is the active matrix, organic, light emitting diode. Right? Why LCD is replaced by the AMOLED? Because with the AMOLED, it's a self-light emitting device. This is the main thing. Okay, LCD you need a backlight. So the liquid crystal in LCD is just doing the control of the passage of the light, so that depending on the amount of the passage, amount of the light which has been passed through the liquid crystal, that is going to be connected to the red, green, blue, okay? 3 elements of the light, so that we can have a display in LCD. So in LCD, it's not a self-light emitting device. It's voltage driving, and it has to have a backlight. But in AMOLED, is a current driving device. And it's a self-light emitting. So it does not need a backlight. So we can have a flexible display, and we can have a transparent display. Okay? So in the old days, the display has to be big and big and big, as you can see in the TVs, screens and notebooks and things like that. But these days, we do not need a big displays. We need a smart displays, like flexible, curved, things like that. And those kind of devices can be realized only by the AMOLED, not by the LCD. So the trend for the displays is moving from the LCD to AMOLED. Now the problem is, in LCD, it's a voltage driving, so that you can use amorphous silicon, no problem. Amorphous silicon is okay. Okay? But in AMOLED, is a current driving and electron mobility. Okay? Electron mobility has to be greater than the 20 centimeters square per volt-sec. Otherwise, you need a very big area for the current, because it doesn't need a certain amount of current for the light intensity, red, green, blue, or depending on the colors, it doesn't need different amount of the current passage through the diode. So at least the electron mobility has to be greater than 20, and as you see, the amorphous silicon is only 0.5, and the polysilicon, depending on the grain size, it can change from 50 to even 400 is possible. And the single crystal silicon is a material property which is 1 to 1420 centimeter square per volt sec. Okay? So for the AMOLED, it does have to be a polysilicon TFT, and then we have a problem here. If you use a glass substrate, then you have to heat it up to 700 degrees centigrade for 8 hours to transform the amorphous silicon into polysilicon in solid state. Okay? And the silicon, the glass cannot put up with that high temperature for that long time. So we have been knowing that AMOLED is very much advantageous in device application over LCD, but we do not know how to make a LTPS, low temperature polysilicon, so that LCD has been the main device for the displays, and so far, okay, up to now. And from early 1995, from Japan, many Japanese researchers has been focused on this LTPS process, and they have been trying the laser scanning technique for the LTPS. So from 1995, okay, Japanese, 7 companies. The Japanese are the these 7 companies are head of all the technologies, LCD technology and so forth, and they have focused on the LTPS since 1995 because they have been the best in these technologies, and they try to use the ELS, that is excimer laser scanning, and what they do is this: if this is a glass, and then they put it just 1,000 angstrom of silicon, okay, and then they use a laser beam focused in the microns, about 10 microns in the size, and then they just scan all over. Then what's happening is that this spot is going to be melted because the focused laser beam, okay? And then when it moves to the next site by scanning, then this is going to be frozen. So melting and freezing, it's going to happen along the scan directions, and then we can have a polycrystal of silicon. Okay? But the problem with this is the dimples. Okay? In early 2004, 2006, and 2010, in these years, many researchers have been focused on how we can reduce the dimples. The dimples happen because on the top view, this is the spot size, okay? Let's say this is 10 microns. 10 microns. And then when you focus the laser beam on this, it should have a Gaussian profile, which means in the light intensity is going to go like this, okay? So the temperature at the center is the highest, and then at the edges of the spot is going to be lower than the central spot. And then when it moves so that it's going to freeze, then it's going to freeze from the outside, the circumference of the spot. And then when it when it becomes a solid, then it's going to be condensed. I mean, the volume is going to be shrinked, so that at the center, the liquid is going to be merged at the center, so that you end up with some kind of dimples like this. I just draw this for the laser intensity on the spot, but you are going to almost the same figure as a dimple after the scanning. So when you scan the laser from this direction to this direction, then you're going to have dimples, something like this. And then with the scanning of this, you are going to have dimples all the way, something like this. Okay? And then the total thickness of the silicon is just 1,000 angstrom. And the dimple height is close to 1,000 angstrom. So that the surface becomes very rough. So surface roughness is the main problem with this laser technology. Surface roughness is the main problem. You have to do some semiconductor processing after this crystallization. You have to crystallization, and then you have to do some semiconductor fabrication for the TFT, right? And this semiconductor processes include the lithography, thin film deposition, and then etching. All those micro patterning process cannot be carried out if the surface becomes this rough, okay? So, as a conclusion, at the late 2009, Japan as a whole, the 7 companies declared that laser technology cannot be used for the crystallization of the silicon deposit on the glass at low temperature without changing the substrate temperature anymore. Laser technology is not an industrial technology. So this is why up to now the Japanese cannot make AMOLED device. No Japanese AMOLED device yet. Right? Who is the who can make the AMOLED displays currently? Samsung. And Galaxy S is the only device equipped with AMOLED screens. No other companies, even in Japanese companies. How can Samsung make the AMOLED screens for the Galaxy S? That's very mysterious, isn't it? Because Samsung never do the research on this laser scaling process, actually. They have enjoyed the money coming from the LCD screens, very big facilities. They built a very big facilities, even bigger than that of Japanese. You know, they Samsung and LG, they make LCD production facilities we call 7th generation in Tangjeong and Paju. Okay? And then that is the biggest facilities ever. So that's a very mysterious, but I'll introduce the only other technologies for the LTPS which has been developed in our laboratory, okay, in my laboratory. And that is MILC, metal induced lateral crystallization. Okay, it has to be nickel. No, I don't know why, but it has to be nickel for the crystallization inductor. And then we have to use the lateral crystallization. That is the characteristic of these technologies. That is the uniqueness of these technologies. Okay? And then I published a paper in 1996, and I'll give you the reference for this. The title of the paper is Low Temperature Polysilicon TFT fabricated by MILC. Okay, and then it has been published in the journal IEEE Electron Device Letters. Device Letters, volume 17, page 162, and it's April 1996 is published. I submitted the paper in 1995. Okay, and then this paper has been cited and awarded from the ISI, United States U.S. Citation Company, ISI Citation Award. It says from 1989 to 1999, during this period of time, this paper has been mostly cited among the scientists. So I got the ISI citation award with that paper. And I hand out you, some of you may have that. I just make 5 copies of that. Understanding of MILC phenomena. It's a review paper. Okay, so I just prepared the 5 copies of this in this class, and if anybody who are interested in this technologies, maybe you can ask me the copy. I can happy to provide the copy of this. Okay. Well, this is the last lecture of this semester, and then where the English lectures in Korea, in the Seoul National University, is always a one-sided lecture. I don't like it very much, but I have to. I want to prepare the lectures in English because we have to consider the foreign students, of course. If we do not have that English lecture, then they don't have much choices. So if I can, I want to provide the lectures in English, and I have kept doing that for last almost 10 years now. And then from last year, I put my lecture contents on the YouTube, so that actually students who are supposed to be busy for their research work don't have to come to the lecture, to spend the time to go and come and go. Okay. And this lecture, we talked about the bipolar and then MOS transistors. And before that, we want to understand the basic physics for the miniaturization of the transistors. And then we covered the electrical properties coming after the miniaturization of the transistors. And then this last lecture, I tried to introduce some of the research work that I've done in my research, because you are graduate students, not undergraduate students. And then I hope this lecture is just helpful for your research work, not just for the grade. As I mentioned in the class, you are going to have grades more than B minus anyway, if you attend the final exam. If you fail to attend the final exam, of course, you're not going to get any credit. So the most important issues of this class is that anything, any ideas, any knowledge has to be exercised on your research work. And that is the most, that will be the happiest thing that I expect from this class. Well, as a last lecture, I want to mention about the inventions in the industries, and I talked about the Samsung briefly. It's a mysterious thing how the Samsung, who never worked on the laser research, can suddenly, in the year of 2010, they just become a manufacturer of the AMOLED screens. It's just a miracle, you know. So when you do the research, whatever, because we are in the engineering school, that has to be oriented to the industries. If you are invention or your idea is just sitting on the table, then I think it is not meaningful for the engineers. Nowadays, the science and engineering has been merged so that we cannot make clear distinctions between science and engineering. But as an engineer, you have to focus on the topics which can be realized in the industry. And then this last lecture may give you some idea how you should proceed on your research. You always have to have light of the industrial terms. Okay, that will wrap up my lecture in this semester, and we're going to see you. We have a dead week next week, and we're going to see you on Monday for the final exam. Okay, that is a 1-hour exam. And then I hand out you the examples of the past exam, and you are not going to have the same questions on your final exam this year. It's just a reference. Okay, any questions? How about your handouts? You have to talk to me? Okay. Okay, I'll see you on 12th. Okay, on Monday.